class for the dog?
What's that?
How was the class for the dog, the training?
Oh, well, that's ended for a little bit, but we've still been just working by ourselves. We've been working on a fetch here recently.
Did it go well?
Yeah. He's getting pretty good. I can start throwing a ball, he brings it back, and then frisbee. He's working on a frisbee, and he can every once in a while catch it out of the air. Yeah, it's fun.
You still give little piece of food after each successful trick, or you stopped it?
It depends. Like for
encouragement only.
For fetch, it's just encouragement, like whatever, happiness and such. But I'm still working on some other tricks. Like we learn how to roll over. So like with that, I use a clicker. Have you heard of it?
Yes.
Yep. So I've used a clicker for like the sit and stay, and for new tricks, I'll still use it for like this like basic sits and stays. Unless it's like a new place, I don't use it as much. They're a lot of work, but they're fun. What methods did you use for your German Shepherd?
Most encouragement, verbal. I stopped giving food as an encouragement, like 4 months old.
4 months?
I used the manual from whatever the police, how to train.
From the police? Oh, cool.
I haven't found it. Very good, thank you. Yeah. Anyway.
Hello. Good. How about you?
Very good, very good.
Ooh, that looks like a lot of things.
No, today will be weakest meeting in the intellectual sense. It will be a lot of writing and a lot of basic math, but it will be really simple. Whom are we waiting? Brendan and Diane, right?
Brandon had to use the facilities.
Facilities?
Bathroom.
Oh, I thought liquid nitrogen storage. It's also facility.
Oh. Maybe it's a colloquialism that I'm used to and you're not.
Well, we'll start earlier because time is limited. Hi, Brendan. How are you?
Good.
Very good, very good. Thank you for great help last time. in the lab. You brought us most important equations.
Oh yeah, the Gifford-Pauli equations.
Yes,
Yeah.
exactly. So today will be a very silly lecture in the intellectual sense, but it will be a lot of writing. So I'll try to speak less and write more. Who we are and what are we doing? We are jumping from low perturbative limit to high intensity perturbation with pulse spectroscopy, where the influence, external influence to quantum system is so strong that it may induce several flips from ground to excited forward and back. And we got acquainted with pulse area theorem that only area under the pulse profile determines quantum state at the end of the story. When we were in the lab, we were drawing spheres. There is nothing new for you, but maybe it's like little memories if you ever need to refresh. And gray box is the Gifford-Pauli equations that we will use today again. So the main goal is to see how the strong, it is not perturbation, strong driving force change state of quantum system. And the main, we are slowing down. We were going like 100 miles per hour and now we will go like 5 miles per hour, pedestrian speed. But there is a reason for this slowdown. We are slowly changing the mindset. Everything we did before was possible to do in the language of wave function, because we always considered isolated system, one quantum system surrounded maybe by driving force or by something that will soak energy from it for relaxation, but it was always one system. From now on, we should start slowly thinking about ensembles, so that there is many similar systems, like in a solution. There are a lot of molecules of the same chemistry, but they have different orientations, maybe a little fluctuation of temperature, and as maybe they some of them move towards detector, some outwards for Doppler effect, and this little changes will affect the overall measurement signal. So once upon a time we will need to make an average over ensemble. But the standard techniques that we are using based on wave function are not perfect to perform this average. You cannot add together wave function amplitudes, right? You need to add together probabilities. And you do not know how to, if there is a in transit, like some superpositional states, also how to add them together in case if we do have average over an ensemble. Therefore, we will slowly, so that there will be no shock, we will slowly depart from wave function and go to the new tools that will be very appropriate for predicting results of measurement, for predicting observables, in case we have an ensemble of many similar systems. So there will, when we will be finishing our meeting today, I'll try to draw a little table with 3 possible ways to predict observables and comparing them on different accounts, on different ways how they're able to predict this averaging over ensemble. So these 3 things, first, generally good but bad for this reason. Wave function based methods. Second, Heisenberg equation of motion based methods, which in this particular case will be optical Bloch equation or magnetic Bloch equation. And which means you write down equations of motion for observable directly. Like if you need to measure your population, you write down how population changes in time, differential equation for population. Or if you need projection of dipole on x-axis, you take this observable expectation value and write down equation of motion for it. That's basically Bloch equation. And the third one is so-called density matrix, which is a replacement of wave function in case we need to perform averaging over an ensemble. So one can make average over an ensemble applied to density matrix and then use it to compute observables. While for wave function you cannot do so. So this is general paradigm, but practical things that we will be doing will be very simple and boring. Lots of writing. Ideal perception of information goes from common to particular, but today we will go from particular to common. We will consider very simple examples, and then we will try to generalize maybe when we meet next time. If you are so curious that you do not know how to waste your free time, there are some other handouts, but there is no requirement to read this, just if you have nothing to do and you need some supplemental information to the materials that we are covering in discussions. And last couple of pages are screenshots from the board from the introductory quantum chemistry that covers this spin projections evolving in time. Same thing as we do right now, but we are doing it on a little higher level. Okay. No more excuses for me to stay away from writing down equations. So, where did we stop last time in the class? I think we considered slightly off resonant system irradiated by harmonic perturbation. We went to the rotating frame. Thinking that our external perturbation is harmonic and the profile doesn't change with time. So it is constant amplitude. We agreed that there is a frequency that describes slow change of occupation between ground and excited, right? Which comes after the rapid. Then we assume that the detuning is 0, and then we found the solutions for C1 of t and C2 of t as function of time, which were cosine to t. I don't remember, was it plus or minus I? Can you recall what was the sign here?
Minus.
Good, thank you. So this is not general. This is particular solution for several conditions, for resonance and for initial condition that at time 0 the ground state is occupied and excited state is empty. But you can get several general trends just by analyzing this solution. So according to Pauli and according to Brandon Gifford, if we are talking about nuclear magnetic resonance, we need 3 projections of the magnetic dipole. We need observables which are SX, observables of this operators is Y, and this Z. So right now, for half an hour, we will stay away from new concepts and just squeeze maximal amount of positive information out of our old friend wave function. So we will find out expectation values of these operators for these solutions of wave functions, and just analyze how to interpret it and what are general trends. There was one thing that was forgotten by myself during the lab, or let's say more generous to myself. It was postponed for the future. After we solve for wave functions in rotating frame, which is simplification of interaction representation, if we do want to find expectation values, we need either assume that operators are time dependent, not assume, we need to explicitly bring time dependence, we need operators in the rotating frame. Or if it is too much of intellectual challenge for us, we need to return back to Schrödinger picture for the wave function, which we didn't do yesterday. Actually, if we do it, then the figures on the sphere will be much more massive than we do. Yesterday we did a good thing, although not very correct. So how do we return from rotating to Schrödinger? Basically, each state accumulates phase according to its energy, right? Trivial evolution. C T equals T times E plus 2 H bar E1T C2 Okay, so actually we need to find observables for this wave function if we do not want to learn what are time-dependent operators. I want to introduce a little simplification that does not change physics or any observables. If you do electronic structure calculations and find energies of orbitals, the important thing is difference between energies. But absolute value of individual orbital is not so much important. Same here. So instead of turning 0 E1, E2. You can redefine it as E2 minus E1 divided by 2 is minus, E2 minus E1 divided by 2 is plus. Which means from E1, E2, we went to our energy origin is somewhere unspecified. We reset the origin in the middle between them. Reset origin. And we can call this like delta E equals plus minus. I hope you permit me to do so. No objections. And in calculations, it will save us a lot of space, and it will not change any of the results. So here, I put delta E by 2 is minus, and here delta E by 2 is plus. So they are accumulating phase in the opposite directions. Okay? Since this one is positive, and here sign up front is negative, I keep this negative. Since here it is negative, I flip the sign here. So for each operator, we are going to apply row by column, right? C1 star, C2 star, 0, 1, 1, 0, 2, C2. I'm debating about asking someone to help, but it is too simple. I can do it myself. I will ask you guys for complicated stuff. So, row by column will be C2 star, row by column C1 star, bra times K. Oh, no, not two. C2. Which will be C2 star C1 plus C1 star C2. Right? I'm going to practice this simple thing in general case, and then we will plug in the solution instead of C and C star, and analyze the solution. Whew. S, Y, T. H1, 2, C1 star, C2 star, 0, 0, C, H1, 2. Here we have minus I C2 star plus I C1 star is bra, and then C1 C2 is kept. I don't know if I should, but I can multiply numerator and denominator by I. Then for the first, it will be I times minus I minus with another minus u. So you do plus C2 star C1 plus C minus C1 star C2 divided by 2. Right? Please check. I make errors like this. Even for the inversion. Practicing roll by column once again. Now it will be C1 star, C2 star, minus C2 star, C1, C2 equals H1 2, C1 star, C1, minus C2 star, C2. No objections. We want to practice laziness as much as possible, wherever it is allowed. It is always better to write one symbol instead of four. Therefore, we can redefine omega rightly divided by 2 times time as pulse area. Right? The larger the pulse, the further the propagation. Now, here we can redefine now this is visible. Now we can redefine the I or H bar times delta over 2t as 5. So it is accumulation of the phase just for trivial evolution. And if needed, we can always return back to physically meaningful notations. Otherwise, we will be just covering a lot of area as painting rather than good senseful relations. So in these notations, our C1 is cosine theta times E plus I phi. C2 is minus I sine theta times E minus I phi.
Why is there an I? You already have I in the definition.
I shouldn't do so. Let's remove I from the definition. Good I, thank you. Good I, quote the I. So I'm going to do nothing except plugging in these solutions into these expressions. Something wrong?
Or you lost your negative on C2.
Very good. But here it is.
Yeah.
So let's plug in whatever we have. C2 star. C2 star means we change the sign plus I sine theta E plus I phi. So this was C2 star. Now times C1, which will be cosine theta times E plus I phi. Okay. I hope you do not need help today. Oh, it is problem. It is not easy to erase help announcement.
I think they learned from last time.
Okay, let's keep going. Sine is plus. Now we do C1 conjugate. Cosine theta E minus phi. You flip this in here, okay? Times C2 without conjugation. Minus 1 sine theta times E minus phi. Close the bracket. So what do we see here? Sine theta times cosine theta can be placed out of brackets. And we can recall that sine times cosine is a sine of double argument, right? So h bar 2 half sine of 2 theta. And then in the brackets, we do have I times E plus 2 I phi minus I minus I E minus 2 I phi. Right? Signs in front of the phi were plus and plus in the first term, minus and minus in the second term. We can always multiply by minus I numerator and denominator. Minus E minus 2 divided by 2i. So if multiplied by minus I, the numerator and denominator to remove I here, and as a price, it should also have minus sign.
No, because a negative times a negative is positive.
Okay, good. What do you have in the brackets? According to Euler. When there is a plus, it will cosine. When there is minus, it is sine. It is sine 2 phi. So S sum x equals h bar over 2 sine 2 theta sine 2 phi. done with S sub S. Now we are going to practice the same exercise for the rest of observables. So we can repeat the terms. First and second term are same as there, and there is just 2 points of difference. There is a minus sign here, and there is a I factor in the denominator. Right? So we can skip previous, just go to second from last step and make these 2 changes. Swap the sign between them and multiply by a factor in the denominator. Over to I sin theta plus E minus divide by I squared. I squared comes from here.
So do you take that into account with h over 2I?
Oh, okay. And then, so because of this I square, we are getting minus sign in front, e power over 2, sine 2 theta is not changed, and here we have Euler formula. Okay, that's the exponential 2 by plus exponential minus 5 divided by 2. This will be Euler expression for which function?
Cosine.
Cosine, yes. S sub y will be h power over 2 sine 2 theta sine 2 phi. So we are done with the second. What is interesting? Well, speculating is always more pleasant than deriving.
There's a 90-degree
Yes,
change.
and they both are real. So we spend so much time messing with imaginary unit, but observables are real.
I think the code that Dayan was using, the P, Y, P, X, and PZ, is incorrect.
Therefore, I didn't announce and didn't invite
Okay.
everyone to use it. It was just a test.
Because it says imaginary units rule is ignored when you.
Well, if by definition all variables are complex there, and it may have imaginary component equals to 10 to the minus 16, which is like 0 on numerical.
Yes.
Okay, and then the last one. Sub z, h power over 2, c1 star cosine theta e minus I phi times c1 cosine theta e plus I phi. Very good. See, so plus and minus will cancel. Minus C2 star. Imaginary unit is the same because of conjugation. Sine theta imaginary unit for each sign because of conjugation. Times C2 minus I sin theta E minus I phi. So these phase factors phase accumulated in opposite direction cancels. I times minus I will be 1. Okay. H bar 2 cosine square theta minus sine square theta. Can one represent it as a product?
Cos 2 theta, or
How do you like?
something like that.
So we have 3 boxes with solutions. It is not general solution, it is specific solution for observables, for isolated 2-level system perturbed by resonance driving force with constant amplitude. But right now we can do the same thing as we did in the lab. We can draw 3-dimensional figure where at each point of time we will draw a vector with x, y, and z projections found according to these images and see which trajectory, which 3-dimensional curve does it plot. So if we assume omega r approaches, so whatever values of sine and cosine theta are set up are not changing. Then S sub z doesn't change, and Sx and Sy change in time according to accumulation of this azimuthal phase, or trivial quantum motion. So if you look only on the Sx and Sy, you have 0, you have Sy non-zero and S-axis is 0. Right? And as time passes by, the Sx growth and Sy decreases. Which trajectory will it do? So one cosine, another is sine. How do you call this figure? This shape?
Isn't it this one?
Huh? Circle. No. It is not shown in the lab. In the lab,
In not lab, I mean.
in the lab we
Regular.
missed conversion to the Schrödinger picture. So we actually missed this trivial evolution. So circle in SZ equal constant plane. Okay. What does happen in the, how does S sub z changes with time? Same as the Rabi oscillations, just cyclically goes up and down. So let me practice the best of artistic skills and draw it. Well, there is something that I do not want to show and prove and derive, but if you look on these solutions, and if you find s x squared plus s y squared plus s z squared, you find that it doesn't change in time, that it is a constant. So where should we sit on this sphere if system is in the ground state? So if the angle theta, no, I'm not sure if,
Should that be when?
in the way how we define it, it will be in the upper point, right? So for, it will correspond to state 1, and this one for state 2. Well, maybe it would be more reasonable to flip the axis so that the ground will be in the bottom and excited to the up. It is a little confusing, but okay.
This is how they do it in NMY. It's up, and then when it goes, it flips down. And
Okay, so let's keep it as it is. So if it is, if system is in the ground state, then we start in the top, right? Then, as we are in the very initial steps, the SZ goes down a little bit. And then at a given value of SZ, it goes to oscillate with Sx increasing and Sy decreasing, so it goes this way. And at the same time, it starts going lower and lower in Sc. So it's like around the globe journey, but in a spiral trajectory. Instead of going one complete circle, some crazy traveler decided to cover longer trajectory on the globe. And if the theta angle will be corresponding to pi pulse, then it just completely converts to the excited state. So go from one pole to another pole. But typically, once it goes completely one Rabi cycle, it happens like 100 rotations in the XY plane. Good? We are not going to get much more intellectual contribution. We are going to keep writing more basic math. But where we are now and what are our goals? We are going from particular example to general. We are going to generalize when we meet next time. Right now we have a particular solution only for this system and for some specific conditions. But we keep in mind that it is an isolated system. if you want to describe realistic experiments, we need an average over an ensemble. And if we do it in based on wave function, we need to, for each representative of an ensemble, we need to solve the wave function, found an observable, store, and then repeat again for each system. If ensemble is 100 representative, we need to find wave function 100 times, and then add summation. There is a wish to simplify and find characteristic of the whole ensemble at once, then find observable, and then report it and compare it to experiment. By now, we have covered only one of the three, wave function. There are two others. Heisenberg equation of motion and density matrix. We are going to skip Heisenberg/Bloch equation for next time and start concept of density matrix today. So it will be, we are not going to define, we are not going to do general definitions and general equations. We are going to get it through hands-on experience. So it is more like lab or practical for solving problems rather than lecture. So we will go bottom-up way. So, do we have any intelligent observations of this procedure, with understanding that we are not looking at it as example, but can we find something general in this path that we did?
My equations?
Well, in this board.
Oh,
your
okay.
equations, your equations are there.
Yeah.
And a little bit of generalization. For example, when we went from Sx to Sy, we identified that the combinations of the wave function expansion coefficients are the same here and there. We just change a factor in front of them. Okay? So when we are going through the path to compute observables, we do not use actual wave function. We always use wave function conjugated coefficient and wave function without conjugation. C squared or C star times C. So we use specific products of the wave function expansion coefficients. If we need these products, why do we solve equation of motion for wave function? Can we identify these products? And write equations of motions for those? Well, it could look silly because there are just two, in this example, there are just two components for wave function and there are four of these products. But as an experiment, we can do it. Because for observable, we do not need wave function, we need these products. So I suggest to follow the goal of looking at these four objects, four projects, and figure out what are equation of motion for them, what are differential equations that define their evolution forward in time. Maybe, I do not promise, but maybe we will observe that it could be more beneficial than wave function for some specific purposes. Make sense about the goal? Please ask now if you disagree or if there are questions, because after this moment I will be just writing like crazy without thinking. No? More or less agree? Okay, I'm going to take a screenshot of the left board and then write there. Well, technically, we need notes for future. We can use screenshots from this video recording, but it is very low resolution. If you were watching them, one can barely see what are the symbols. So, C star 1, C1, C2 star C2, C1 star C2, C2 star C1. So we are going to practice this little exercise, and we hope that it will give us external benefits. And before we do it, let's recall how the equations of motion for standalone coefficients look like. So minus I over h bar delta E over 2 C1 minus I over 2 omega R C2 dC2 dt minus I over h bar. In one case it should be one side, and another is different side. So 2 minus I over 2 C1. And if you do C star for the conjugated, then all signs are flipping in front of imaginary unit. Minus I h bar delta E over 2 C1 star plus I over 2 omega R C2 star d dt C2 star, flip the sign, plus I h bar delta E over 2 C2 star plus I over 2 omega R C1 star. It's just for reference. You can keep it just in your head, but it is easier to do copy-paste operations than record from scratch. Now, derivative of a product is what? Is derivative of first times second plus first times derivative of second. Right? Derivative of first times second plus first times derivative of second. Derivative of first times second plus second times derivative of first. Derivative of first times second plus correct? Now we are going to plug in the expressions for derivatives. Let's see what happens. And just in case I need to continue a long time, I will make a short of a second word and then do it very long. So you can plan and reserve space in your notes if you are taking notes. Okay. Derivative of the C1 star. So I'm going to take this expression and plug it into here. minus I over H bar delta E equal to C1 star plus I over 2 omega R C2 star times C1 plus C1 star. And now I'm going to plug in the box from there. I over H bar delta E over 2 C1 minus I over 2 omega R C2. Now let's open the brackets. So first, minus I over H bar delta E over 2 C1 star C1 plus I over 2 omega R C2 star C1 plus I over H bar delta E over 2 C1 star C1 minus I over 2 omega R C1 star C2. So before we go forward, do we have any observations? How do we both on the first and third term? They have the same combination of the wave function expansion coefficients and opposite signs.
Cross them.
Yes, thank you. I over 2 R C2 star C1 minus C1 star C2. Okay. Now let's no, it is too simple. I will ask someone to help on next lectures where we will hard stuff. What I'm going to do now, so we need C star 2 derivative. So we need this box. Copy paste into here. Plus I H bar delta E over 2 C2 star plus I over 2 omega R C1 star times C2 plus C2 star, and now I need the box for C2 without derivative. Oh, first for C2 with derivative but without star. Minus I over H bar delta E over 2 C2 minus 2 R C1 close the bracket. So now we are going to open the brackets and see if it will look a little simpler or if one can combine any terms together. Plus I over H bar delta E over 2 C2 star C2 plus I over 2 omega R C1 star C2 minus I over h bar delta E over 2 C2 star C2 minus I over 2 omega minus I over 2 first, second, third, fourth omega R C2 star C1. Well, there are no terms to cancel, but there are some similarities. The first and third refer to the same product of the wave function expansion coefficients, right? And the factors up front have different signs.
So why can't you kill it?
Yeah, why can't you cancel those two?
Yes, we can cancel. Good. Perfect. And here we can just put I over 2 over there up front. And here C1 star C2 minus C2 star C1. So it's very similar to, compared to what it was in the previous line. Okay. As soon as we finish these two lines, you have just one little thing to, until the end, to draw a little table of comparison. So it will be done really soon. Just a little effort to go through this one.
Levi said he really wants to write this one out.
Huh?
Levi said he really wants to write this one out.
I think that's Brendan volunteering himself.
Phyllis.
I know how to satisfy both of you. You can set up a homework.
See, Brendan, this is what you do. I'm trying to work on the MATLAB code, and
I'll do it. It is still seems too easy. So, number 1 star, 1 dot. So it is black box from here. I'm going to copy paste this stuff into this bracket. Minus I over h bar delta E over 2 C1 star plus I over 2 omega R C2 star times C2 plus blue box from here. No, wait. C1 star times C2 without star. It is in the red box from here. Right? Okay, wait. Minus A over h bar E over 2 C2 minus I over 2 omega R C1 close the bracket. C2 plus I over 2 over C2 star C minus I over h bar delta E over 2 C1 star C2 minus I over 2 omega R C1 star C1. in the last two terms they will be a little longer. Nothing will be cancelled, but we do see that we can combine terms that have the similar factors up front, just for shorter notation. So we can do I or 2 over R of C2 star C2 minus C1 star C1. And you can minus I over H bar delta equal to C1 star C2.
Instead of E over 2 is just E. Probably
1 and 2. 1 and 2.
Yeah, so you get a factor of 2 and now kill 2.
Yes! Yes!
That's what I
like
said.
it.
I know, I was agreeing with
Oh, you were- So you cancel factor 2.
you. I was agreeing with
Let's keep it this way. Very good.
you. No.
But you couldn't do attention frame.
So if we want to notice where we started from, it is a time derivative of the product C1 star C2. So it will reproduce itself with the factor here. So it will be like trivial place accumulation.
Wouldn't the next one be the exact same, but you just switch the indexes?
Yes. But do not deprive a pleasure of writing a long line from me.
They told you he wanted to do it.
No, I don't. I just.
You'll have your chance. Or we can compete. I. Who wants to write this long line? So, which box do we write now first? C2 star is the ring. Red box. Times plus C2 star. Which box do we copy now? The first blue box. This one, right? Should be over H bar delta E over 2 C1 minus I over 2 over R C2. C2 star C1 plus I over 2 over R C1 star C1 plus I over H bar delta E over 2 C2 star C1 minus I over 2 so far, C2 star C. No errors yet. Now let's see if you can combine it in a reasonable way. So probably the terms that change occupation of levels with radio frequency here and there can be combined as I over 2 over R C1 star C1 minus C2 star C2. same as in the previous line, but with opposite sign, right? So difference of populations between ground and excited. And then the rest, so it is, do we see Brandon's discovery again? So that we can merge
Yeah.
them together.
Yeah,
So
but now it's plus.
C star 2 C1, C star 2 C1. And the positive, so the factor 2 will be cancelled. Plus I over H bar delta E C 2 star C1. Whew.
I'm exhausted. I'm doing
Well, I hope we do not do this long lines until the anymore. But general introductions, general things will be much easier. It's just practical application that took longer time. So absolute value square of wave function is interpreted as, okay,
probability.
I'm going to ask a question. I'm going to give a verbal formula and ask you to give it a name. Absolute value square of wave function.
Probability.
Good. So the common interpretation of quantum mechanics is that wave function square gives probability. If you are doing computational chemistry, especially density functional theory, how do you interpret wave function square?
Charge.
Yes, density.
Yeah.
Density of charge. Good. So two opposite. You see, each term that we dealt with include wave function squared. So we can, and it has two indices. So we can either call it probability or density. You can call it probability matrix or density matrix. So let's call density, and we are going to swap the order of indices. Whatever was second will be first, whatever was first will be second. This will be row 1, 2. This one will be row 2, 1. Then those are the same, and here this one will be row 1, 1. This one will be row 2, 2. Now let's summarize all our achievements in the last half an hour and rewrite these long lines in a short notation. So row 1, 1, row 1, 2, row 2, 1, row 2, 2. DT. So for row 1, 1, how can we write it down? I over 2 omega r row 1, 2 minus I over 2 omega r row 2, 1. Correct? For the row 2, 2, which is the meaning of this density is a population in the excited state, in the state 2. So, um, two, four, 2, 1. Will be minus I over 2 omega r rho 1, 2 plus I over 2 omega r rho 2, 1. So we are done with the first and last equation. And now we need two more. So this one will be for rho. So this is simple, and this one, if we use this rule of slope of indices, will be rho 2, 1. Rho 2, 1 equals minus I over h bar delta E times rho 2, 1. Which other terms do contribute to it? I over 2 omega sub r plus minus rho 1, 1 plus I over 2 omega sub r rho 2, 2. 3 terms. And we have one equation left for rho 1, 2. So we do have a term discovered by Brennan that corresponds to trivial accumulation of phase. So if it is rho 1, 2, it will be rho 1, 2 in this term. So, minus I over h bar delta E rho 1, 2. And there will be 2 terms more. Plus I over 2 omega r rho 1, 1 minus I over 2 omega r rho 2, 2. So what did we get, and what is the meaning? What are the benefits? What is the value of what we got?
Change of the density over time.
Huh?
Change of the density over time in the difference.
Yes. It is a question of motion for density. But the main benefit is that if you have ensemble of several similar systems, you can solve, or not solve, just write down equation for density of system 1, system 2, system 3, add them together, solve at once, and then this solution will be characterization of the ensemble. So the language of this density matrix is much more appropriate for description of ensembles, for averaging procedures. So this one is the replacement of Schrödinger equation. Right now, in this example, it looks ugly. It looks like 4 times bigger than Schrödinger equation. So the only hope that it is more beneficial, it is the only, it is one of the correct ways to describe average over the samples. Probably we can postpone table for next meeting when we will have higher attendance. But I want to do one thing more, is to rewrite this equation in more appetizing form. Although probably you do not like it from the beginning, but it can be written in a little shorter way. So remember when we were dealing with wave function in discrete spaces, our wave function is a vector, right? Like C1, C2 as a vector. Why don't we consider matrix which one can write as a matrix? 1, 2, 3, but no one forbids us to write this object as a column vector. And if you write down a column vector and we have a derivative of this column vector, then we can write it in a matrix form. So 1, 2, 1. If this is a column vector, and we are going to apply derivative, we see that result is nothing but linear combination of first order of each of the elements. So it is a linear differential equation, right? For each element is linear. And for vector is also linear, which means that we can formulate a matrix which will be 4 by 4. And this matrix will be acting on the same vector of elements of density matrix. Row to 1, row 2, 2. Okay, now it is time for the help. Can you please fill the first row?
The entire first row?
Yes. So convert this differential equation into.
So let's put this here, right?
Mm-hmm. Okay. Mm-hmm. How do you feel the remaining two
Nothing.
zeros? Yeah. Excellent. Many thanks. You right? Will you please help? Excellent. Many thanks.
Your eye out front or something?
You could take I over 2 out.
No. Because I out 2 is negative.
You could add it to
This is a term derived by Brendan. The Jared is writing with him.
This is how you do it.
Yeah, that's the only term. It's the only term. So then what you could do is times that by 2.
Oh.
And write 2, 2 instead of
Yeah, many
I
thanks.
don't want you to do something to waste your time. Just put 2 inside and take a 2 out.
So you got 2 2s. How many 2s do you write now? 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9
It
2s.
looks like a popular song. 1, 2, 3.
9 2s with underscore fractions.
Many thanks.
Times, and you say.
So what do we see here?
Look familiar.
Huh? It looks familiar for you?
I mean,
So there are two terms derived by Brandon that corresponds to trivial accumulation of phase, and these terms will be only present if we do not have the external field. If the system is left to live alone, like spherical force in a vacuum, isolated atom in the space without an electromagnetic field, then will be only these two terms. As soon as we bring in the driving oscillating force, driving oscillating field, then it induces transition between diagonal and off-diagonal elements. So for off-diagonal elements that correspond to so-called coherence, it got increment based from what it was in the either ground or excited populations. And for actual populations, they got changed only if the off-diagonal elements are on zero. So it describes the same processes as we did an hour ago with a wave function. And there is a way to convert it into observables.
Did we make a typo?
What?
Is the 2-1 term, is that supposed to be I over 2 for the second term or I over H bar?
H mark.
No.
Yes, thank you.
There.
Thank you. Yeah. So it is very like if we do vectors of wave functions coefficients, then we can write it as a matrix times vector, and we tell that this will be Hamiltonian matrix. Everyone wants to be famous, and it cannot be that no one claimed name for this matrix. So if we write d dt for the rho as a vector, no. And since it has a dimension n squared compared to the like here it was 2 by 2, like n by n, and n by n, and here is n by n by n by n, n to the fourth. So it is something bigger than operator. It is super operator. Which super operator? Super operator. I think it is enough for today. We are seeing more than I intended. But thank you for your patience. Thank you for collective derivation of the main equation, and see you next week on Tuesday. Meeting number 18 is complete. Is dismissed. You are free to leave, and I will just stay and answer questions if there are any of those.
All that algebra takes me back to my days when I was working with Pauli on the operators.
Mm-hmm.
Ollie.
You know, Gifford Pauli operations.
Oh, I have a friend whose last name is Polly. That's how you draw a circle with